Next generation wireless communication in millimeter wave band and beyond is directional to overcome the increased attenuation in high frequency regimes. To establish a directional link, wireless nodes need to align or train their beams toward each other. This training typically includes sequential transmission of beacons under different directional settings, while the other node is measuring the received power with an omnidirectional beam and identifies the best beam configuration. For a fixed client, like a smart TV in this example, this training needs to happen only once. But for mobile use cases, constant training is required to guarantee seamless connectivity. The problem of directional beam coordination becomes even more challenging in terahertz frequency band. In practice, given that terahertz links lack the omnireception capability available at millimeter wave, the previously mentioned trial and error technique cannot be applied. Further, terahertz beams are inherently more directional with narrow beams of only a few degrees, which significantly increases the number of possible sender-receiver beam combinations and the overhead of exhaustive testing. Finally, as beams become narrower, links get more sensitive to blockage or mobility, which demands for fast adaptation techniques. But what if we had near-instantaneous knowledge of the physical paths, including line of sight and any potential reflections between the access point and all clients? In that case, nodes can instantly steer their beams toward the line of sight directions. In a blockage incident, they can redirect their beams toward a potential reflector. Also, nodes can efficiently realign their beams as they move. But how can we get such valuable path information in mobile terahertz networks? In this paper, we present OPERA, a one-shot path discovery with a THz Rainbow. OPERA's goal is to identify high-rate physical path between any two nodes in real time. The key idea is to simultaneously transmit distinct signal with unique spectral signatures across the spatial angles such that each physical path gets its own signature. To create such unique spectral signatures in each direction, we introduce Leaky-Wave Antenna to the terahertz control plane. Leaky-Wave Antenna is a metal parallel plate waveguide with a narrow slot open on one side. Leaky-Wave Antenna is a passive device. It's small, light, and cheap, and hence it can easily meet the power, size, and weight consideration of handheld devices. This device allows a traveling wave inside the waveguide to leak its energy out into free space with a unique property that the emission angle from the waveguide is coupled to the frequency of the input signal via a closed-form relationship that is rooted in the physics of the waveguide and boundary condition. This relationship suggests that the higher the frequency, the lower the emission angle would be, and vice versa. This property makes this device a promising candidate for steering in frequencies above 100 GHz. However, we are still left with the problem of where to steer. To solve this problem, our key idea is to transform this property of angle-frequency coupling into a one-shot spatial signature. To do this, we excite the Leaky-Wave Antenna device with a terahertz pulse, or equivalently a broadband signal in the frequency domain. Once the pulse reaches the beginning of the slot, different frequency components decouple and emerge at different angles. This would fill the space with signals that have unique spectral signatures or color at each direction. That's why we call this pattern a THz Rainbow. Then we develop a model based on the physics of the waveguide and terahertz wave propagation that enables the receiver to correlate the spectral properties of measured signal with path directions. To summarize, OPERA achieved real-time path discovery and tracking with a single-time transmission of a terahertz pulse, which is itself in the order of nanosecond. OPERA has a single antenna design because it requires one Leaky-Wave antenna in the control plane. Our path discovery scheme is non-coherent as it uses only power measurements at the receiver and not phase information. This eliminates the need to keep tight synchronization between the transmitter and receiver and makes our scheme robust to small-scale channel variations. Finally, path discovery in OPERA is scalable such that all clients can simultaneously and independently identify their path information by analyzing their received power spectrum. If you are interested to learn more about OPERA, please check out our paper. Thank you.